I'm on neutron characteristics. Now, by this time, it's actually going to seem like review, right? So how can we characterize a neutron? Well, we've already talked about several, and this is going to be review now, all right? So review, how can I characterize a neutron? Well, first of all, it says by origin. Neutrons that are produced from neutron-induced fission are called fission neutrons. Okay, there's a big duh. But if the neutrons come from someplace other than fission, we call them source neutrons. So there's a possibility of fission or source. That's their origin. We're going to talk about this much more in Chapter 3, but they're fission neutrons or they're source neutrons. And then we'll talk about different sources as well. We'll talk about 3 sources of neutrons in our core that don't come from fission. Also, if you look at the next thing, so their origin. Before I go on, origin, neutrons could be classified as fission neutrons or source neutrons. They have to be one or the other. Then I could classify a neutron by its energy level. And we already know greater than 0.1 MeV is fast. Less than 1 EV, so that's 1 to 100,000 right there, right? This is called slow neutron. And if I'm in between greater than 0.1 MeV, greater than 1 EV, but less than 0.1 MeV, we had 2 names for this. We called it intermediate neutron. You go ahead and spell it out. Or remember, we called it epithermal neutron. That was that area right in between fast and slow, epithermal or intermediate. So that's 2 ways. I could have a fission neutron at 200,000 electron volts. Origin is fission, and it's in the fast energy spectrum right now. That right there, all by itself, says we're going to talk about origin, source neutrons, but look right there, there's a K and A. Define a fast, intermediate, and slow. That is all by itself, just looking at what the kinetic energy of the neutron is. All right, next, I can define a neutron by its production. That means where it came from in terms of time. So it's production time. So let's look at a neutron here. Neutron comes in, interacts with uranium, causes fission fragments to be created, and here's a neutron. If that neutron is born within sooner than 10 to the minus 14th seconds, that neutron was born almost immediately. I mean, it was on time. We're going to call that, if it's less than 10 to the minus 14th seconds from the fission event, that it showed up in a prompt fashion. We saw it almost immediately. You can guess then that there's going to be something other than prompt in terms of when the neutron shows up. And we're going to call that greater than 10 to the minus 14th seconds. We're going to call delayed neutrons. Delayed. So in terms of origin, I could have a fission neutron that an energy level of 2 megaelectron volts, so it's a fission neutron that's fast, and it was born within 10 to the minus 14 seconds, so it would be a fast prompt fission neutron. Or I could have a fast prompt delayed neutron. I will tell you this, when these are born, both prompt and delayed, either whether it be after or before 10 to the minus 14 seconds, they are generally born fast. They are both born, even though this one was born immediately, it's born with a certain energy level that's in the fast energy spectrum. This one is about, on average, 2 megaelectron volts. The delayed neutron is about 0.5 megaelectron volts. So those are some energy levels that we look at. This is an average energy level of a prompt when it's born, average energy level of a delayed. So they're both born fast. It's just when did they get born? Were they born in 10 to the minus 14th or sooner? or something later than 10 to the minus 14th. The average time for these delayed neutrons to show up, by the way, steady state, is 12.7 seconds. And they're born fast. They're delayed around 12.7 seconds, born in the fast energy spectrum. That's production time. Very key. This right here has to be understood, that we can, just like a person, we can talk about them in terms of their color, their hair, their weight, the color of their eyes, how fast they run. Well, we have different ways to classify the neutron. So production time, very key that we understand this. So delayed neutrons are actually going to be the key to this whole thing. Even though they're born fast, they're born at a lower energy level, and they represent a super, super small fraction of the population we're fixing to find out. They're going to be ultimately important.